Hello, this is Sareen from Exam Help Lab. Today I'll be solving Chemistry Paper 2 AS Level Structured Questions 9701 Paper 2 variant to October-November 2018. Question number 1. The model of the nuclear atom was first proposed by Ernest Rutherford. He developed this model on the basis of results obtained from an experiment using gold metal foil. Complete the table with information for 2 of the particles in an atom of gold 197. So electron is located in outer shells. Neutron has a relative mass of 1 unit. It has a 0 charge. It's a neutral component of an atom. And the total number of neutron in an atom of gold 197 is 197 minus 79, which is 118. Part B, state the type of bonding in gold. Gold is a metal, so that is metallic bonding. Part C, a sample of gold found in the earth consists of only one isotope. Explain what is meant by the term isotopes. So these are atoms of the same element that have same proton number but different mass number. Part 2, a different sample of gold contains more than one isotope, suggest why this different sample of gold has the same chemical properties as the sample found in the earth. So chemical properties depend upon valence electrons, the number of electrons in the outermost shell, and isotopes, they have got only different number of neutrons, which means that they have all got same number of valence electrons, therefore they share same chemical properties. So it's all due to having same number of electrons. Part D, Tembaga is an alloy of copper and gold. A sample of Tembaga was analyzed. The mass spectrum of the sample is shown. Calculate the percentage abundance of gold in the sample of Tembaga. So this is 56.36 plus 25.14. These are the copper isotopes present in Tembaga, and this peak is for the gold. We are supposed to find the percentage abundance for this one. So the percentage abundance of these two copper atoms is 56.36 plus 25.14. which is equals to 81.5%. This means that the rest of the percentage is percentage abundance of gold present in Tembaga, and that is 100 minus 81.5, which is 18.5%. Part 2, calculate the relative atomic mass of the copper present in this sample. Mind that here we are talking about the relative atomic mass of only copper, not Tembaga on whole. So the first percentage abundance of copper present here is 56.36 multiplied by the atomic mass multiplied by the mass, which is 63, plus the second percentage abundance of copper that is present here, which is 25.14 multiplied by its own mass, which is 65, and we will divide by the sum of the percentage abundance of copper present in here, that is 56.36 and 25.14, and this gives us 63.62. This is the atomic mass of the copper present in this sample of Tembaga. Question number 2. The table gives some data for elements in the third period and some of their compounds. Complete the table to show the bonding in the elements and the formulae for their oxides and chlorides. So magnesium has metallic bonding since it's a metal. Aluminum also has a metallic bonding. And silicon forms covalent bonding. Formula of oxides, so this is Na2O, this is MgO, this is Al2O3, and this is silicon dioxide, so SiO2. This is AlCl3, aluminum chloride, and SiCl4, this is PCl5. Part B, SCl2 is formed in the following reaction. Complete a dot and cross diagram to show the bonding in a molecule of SCl2. Show outer electrons only. Sulfur will be sharing 2 of its electrons with these 2 chlorine atoms. that will share 1 electron with sulfur. So sulfur shares 1 with each chlorine atom. These are the chlorine outermost electrons, while these are of sulfur atom. To complete and fully label the reaction pathway diagram for the reaction between S2Cl2 and Cl2, include labels for the activation energy and the enthalpy change of the forward reaction. So S2Cl2 plus Cl2, that gives 2 moles of SCl2, is an exothermic reaction, as it can be seen from here that it has an enthalpy negative. Therefore, energy of products is going to be less than that of reactants, so we will label this as the energy of the products that are forming out of this reaction. Now, this hump, which connects reactants with products, this hump's height represents the activation energy, meaning the least energy required to get the reaction started. So this is activation energy. And from here until here, this is the net enthalpy for this reaction. Part C1, on the axis, sketch the trend in melting points of the elements sodium to sulfur. So melting points from sodium to silicon will increase, where silicon will have the highest melting point. So Na, Mg, Al, and silicon has the highest melting point. Then rest in period 3. Now phosphorus forms P5 molecule and sulfur forms S8 molecule. So melting point of sulfur is going to be higher than that of phosphorus. So phosphorus has this melting point and sulfur will be having this melting point. So now we are going to join all these. Part 2, give 3 statements to explain your sketch. Now melting points, the first explanation would be melting points from sodium to magnesium to aluminium will increase because of increased number of delocalized electrons they all have. Thus force of attraction between them and positive metal ions will increase from sodium to aluminium. Now, second explanation would be related to silicon. Why this is having the highest melting point among all the other period 3 elements. Silicon has got a giant covalent structure and has the highest melting point due to its strong covalent bonds. So sulfur has giant covalent structure and strong covalent bonds. That's why it has the highest melting point. Sulfur and phosphorus have van der Waals forces that are weaker than both metallic and covalent bonds. So melting point for them is lower. Part D, write an equation for the reaction of oxide of phosphor with water. So this is P4O10 plus water. This gives phosphoric acid, which is H3PO4, 4 moles and 6 over here. Part E, sulfur dioxide can be released into the atmosphere when fossil fuels containing sulfur are burned. Statement explain one environmental consequence of the release of sulfur dioxide into the atmosphere. So sulfur dioxide turns to sulfur trioxide, which turns to acid rain H2SO4 when reacts with water. This acid rain poses serious threat to marine life and damages buildings too. So we can write that turns to acid rain, which damages buildings. Part F, the elements in the third period show a general increase in their first ionization energies from left to right. Identify two pairs of successive elements in the third period that do not agree with this statement. For each pair, explain why the change in ionization energy does not agree with this statement. So ionization energy is removal of an electron. Though from left to right, elements ionization energy will increase in period 3, but this is not the case with magnesium and aluminium. This is the first pair. And the second pair is phosphorus and sulfur. In case of magnesium and aluminium, magnesium has its electronic configuration ending at 3s subshell, where it has a complete subshell, complete orbital 3s2, whereas aluminium has its first electron being removed from 3p subshell, that is of higher energy level, that does not require that much energy which 3s subshell would. So we can write that aluminium has its electron being removed from 3p subshell, that is of higher energy level. So lower ionization energy. Now, as far as phosphorus and sulfur are concerned, sulfur has a paired electron in a 3p orbital, that is 3p4. It will be having a 3p4 subshell, and the electrons will repel each other and not much of external energy is required to separate them. So sulfur has an electron pair in 3p orbital that experiences repulsion. And that is why its ionization energy is much lower than that of phosphorus, which has a half-filled 3p orbital. Question number 3, trihalomethanes are organic molecules in which 3 of the hydrogen atoms of methane are replaced by halogen atoms, for example CHF3. The equation shows a reaction to produce CHF3. Use the data to calculate the enthalpy change of reaction for this formation of CHF3. So CHI3 does 3 moles of AgF. This gives CHF3 plus 3 moles of AgI. Now for formation of all these molecules, we are already given their enthalpies. What we have to do here is build a cycle. Formation of all these require elements in their standard state. So I'll write carbon here in a solid form, hydrogen gas plus iodine solid plus Ag as well as fluorine gas. Now, we need to label all these arrows with their respective enthalpies, but before we do that, we need to make sure that all these 3 cycles are balanced. So we will be having 3 by 2 over here, and we are also supposed to have 3 iodine, so 3 by 2 over here, and 3 Ag. Now, for the formation of 1 mole of CHI3, we will be taking this value, negative 182.1, and for the formation of AgF, but 3 moles of AgF, so we will be multiplying this value with 3, so 3 into negative 204.6. Now for the formation of CHF3, only 1 mole, we will be labeling this as 692.9, and for the formation of 3 AgI, we will be labeling it 3 into the enthalpy change of formation of 1 mole of AgI, that is negative 61.8, and we have this as X. Now the enthalpy of direct route is going to be equal to enthalpy of indirect route. The direct route is this, while the indirect route is from here and then here. So negative 692.9 plus 3 into negative 61.8, this is equals to enthalpy of the indirect route, which is from these elements to the final product. So this is negative 182.1 plus 3 into negative 204.6 plus X. Now when you rearrange your equation, you will have the value for X as negative 82.4 kilojoules per mole. This is the enthalpy change of reaction. Part B, the graph shows the relationship between PV and P at a given temperature for CHF3 and an ideal gas. Part 1, CHF3 is not an ideal gas. State 3 basic assumptions that scientists make about the properties of ideal gas. So firstly, gaseous molecules have negligible volume as compared to that of their container. Secondly, molecules do not experience any kind of intermolecular forces, whether it's attraction or repulsion. At last, collision between those gaseous molecules is purely elastic. Part 2, explain why CHF3 deviates from the properties of an ideal gas at pressures greater than 300 atmospheres. That is because CHF3 molecule size gets significant after 300 atmospheres of pressure. Also because they start experiencing repulsive forces among molecules. Part C, a different trihalomethane reacts with oxygen to produce carbonyl dichloride. HCl is also released as a product of this reaction. Write an equation for this reaction of CHCl3 with O2. CHCl3 plus O2 gives carbonyl dichloride, that is COCl2, plus HCl. We have half mole of oxygen gas here. Part 2, the conversion of CHCl3 to carbonyl dichloride can be monitored by infrared spectroscopy. The infrared spectrum of carbonyl dichloride is shown. On the infrared spectrum of carbonyl dichloride, identify with an X the absorption that would not be present in an infrared spectrum of CHCl3. So carbonyl dichloride is C double bonded to O and single to Cl, while CHCl3 is CH and then Cl over here, Cl on 3 sides. This is the absorption we will be talking about. This absorption will not be present in the infrared spectrum of CHCl3 because this strong peak is due to C2O double bond, which is not present in CHCl3. So CHCl3 does not have C2O double bond, so no peak at 1670 to 1740 per centimeters. Part 3 suggests another difference between the infrared spectra of CHCl3 and carbonyl dichloride. Again, carbonyl dichloride is C2O double bond and then Cl, while CHCl3 has CH and 3 Cls. CHCl3 will be having a strong peak due to C2H single bond at 2850 to 2950 per centimeters, which COCl2 won't be having. So CHCl3 has a strong peak at 2850 to 2950 per centimeters due to alkanes or due to C2H single bond, which COCl2 doesn't have. Question number 4, the diagram shows a reaction sequence starting from ethanol. Now reaction 1 over here is aldehyde being added to HCN and NaCN, which is acting as a catalyst. This means a nucleophilic addition reaction takes place, and P has both hydroxyl group and nitrile group. P is then added to dilute H2SO4. This turns a nitrile group to COOH group, which is this one. Rest will remain the same. Reaction 3 is removal of a water molecule, so aluminum oxide as a catalyst was used here. Reaction 4 now is secondary alcohol was replaced by a ketone group, and this was successful due to acidified chromate ion, which is an oxidizing agent. So P we are talking about over here, draw the displayed formula of P. P will now have a hydroxyl group as well as a nitrile group. So CH3, see this ketone, this aldehyde group will break into a secondary alcohol group, a hydrogen over here, and a nitrile attached to it over here. Part 2, name the type of chemical reaction that occurs in reaction 3. So reaction 3 was removal of a water molecule out of this is structure Q. So this is dehydration. Part 3, write an equation to represent reaction 4. So CH3, COH, H, and COOH. This gets oxidized to CH3, C2O double bond, and COOH. Now carboxylic acid cannot oxidize any further. This must have been already oxidized from a primary alcohol. Now to balance our number of hydrogen and oxygen, we'll add a water molecule to this side. Part 4, state the reagents and conditions for reaction 4. So reaction 4 would require us to add acidified potassium chromate, which is K2Cr2O7, because that will act as an oxidizing reagent over here. Part B, compound Q is formed as a mixture of two optical isomers. Part 1, explain what is meant by the term optical isomers. So optical isomers are molecules that are non-superimpulsible mirror images. Part 2, draw the two optical isomers of Q showing clearly their three-dimensional structures. So structure Q has the hydroxyl group and carboxylic acid group. So this is COH, this is H, and this is CO2H, and this is the methyl group. Now on the other side of this symmetry, we are going to have again COH and H over here. Well, we'll have COH and CH3 here. Part C, R can be used to make a polymer W in two steps. Draw one unit of W. So R is an unsaturated molecule with a carboxylic acid group. So C to C double bond, H and H, OH, COOH. When this undergoes addition polymerization, this will turn into C to C single bond, and this will form two new single bonds. And when this reacts with NaOH, because this is an acid and this is an alkali or a base, when a base reacts with acid, this forms a salt, COO and A. So the repeat unit for W is going to be C to C single bond and COONA, and 2 new sigma bonds with N over here. This is the repeat unit of W. Part D, compound Z is produced from R. Z can be used in a two-step process to produce 2-aminopropane. In the first step, Z reacts with HBr to form 2 products. The structure of the product depends on which intermediate is formed, intermediate 1 or intermediate 2. Explain why intermediate 1 is more likely to form than intermediate 2. Okay, so the difference between intermediate 1 and intermediate 2 is that the carbon, which gets a positive charge, this carbon over here is attached to 2 methyl groups, while this one is attached to 2 hydrogen groups. This means that this forms a primary carbocation intermediate, and this one over here is a secondary carbocation. Now, secondary carbocation is more stable than the primary one, because this one has more alkyl groups attached to this carbon atom, which also carries a positive charge. So due to them, there is more positive inductive effect, and hence that makes the positive charge on carbon atoms more stable. So this is why intermediate 1 is more likely to form than intermediate 2. So I can write that intermediate 1 has more alkyl groups, so due to them, there is more positive inductive effect, and hence that makes the charge on carbon more stable. Part 2, when intermediate 1 forms the product of the first step is T, complete the diagram to show the mechanism for the conversion of Z to T. Okay, so this double bond between these 2 carbon atoms is electron dense, which induces partial positive charge on this hydrogen atom, and Br gets a partial negative charge. This bond this way breaks heterolytically, so an arrowhead towards Br. This intermediate with a carbon carrying a positive charge will be attracted towards bromine that has a negative charge and a lone pair of electrons. So this will be attracted towards this C, which has a positive charge on it. Now, part 3T can be converted to 2-aminopropane. Name the mechanism for this reaction. So this is nucleophilic substitution reaction, because NH3 is acting as a nucleophile over here. And Br gets substituted by NH2. E part 1 compound S can be reduced by LiAlH4, which is a reducing agent. Complete the equation using structural formula to represent this reaction. Use H to represent the reducing agent. So compound S has a displayed formula of CH3, C2O double bond, and COOH. Now this one reacts with LiAlH4. This ketone group will reduce to secondary alcohol. So this becomes COH, and this gets a hydrogen over here, and COOH will reduce to primary alcohol, thus it would be CH2 and OH. So this one reacts with the reducing agent. We get CH3, CH that has a secondary alcohol group, in CH2OH. Now to balance our equation, we will add a water molecule to this side and a 6 over here. Other reducing agents containing group 1 metal cations include LiBH4, NaBH4, and KBH4. The strength of the reducing agent depends on the side of its cation. Give the electronic configuration of the sodium ion cation. For a configuration of an ion, you should be writing first the configuration of its neutral atom. So sodium neutral atom has an electronic configuration of 1s2, 2s2, 2p6, and 3s1. So that of sodium ion would be, you'll be taking away 1 electron from the highest energy level possible here, which is 3s. So 1s2, 2s2, and 2p6. Part 3 suggests why ionic radius increases down group 1. The number of electrons though increase when we descend group 1, but the number of shells also increase, and shielding of outermost electrons increases, which weakens force of attraction between valence electrons in group 1 and the nucleus. Thus radius of the ion increases. So we can write that as the group is descended, ions have more shells. So that was the end of the paper. Thank you for watching.